Okay, so today we're just going to define heat, work, define power. So let's do heat. Let's do heat first. All right, so energy transfer by heat. So in thermal and fluids and all other ones, we call them Q, which is kilojoules, or BTU, British Thermal Unit. We can have little q, just Q over M, and yes, between what? And I'm not even going to give you the equations for the three modes of heat transfer. Can you remember what I told you a while ago what they were? Yep. So conduction, convection, and radiation. Okay? We are not going to cover those, and I'm not going to give you the equations. So for thermal, that's one class. That's heat transfer. For thermal, the only thing we're going to do is if it's looking for, basically the problems are either going to ask for it or I'm going to give it to you. Okay? So the other things I'm going to show you for work later on, though we have equations for, okay? Because I want to split that up. It's easier to learn it that way first. So all the homework problems there should be no like, okay, use the conduction equation. Nope, I'm not doing that, all right? Okay, so those are the units. Heat transfer goes from hot to cold. Remember that. And the last really thing I want to talk about heat is, then I'll show you one equation that's not those equations, but an adiabatic process. Remember what that was? Pretty sure I remember telling you. I'm not that old yet. Adiabatic. Not ringing any bells. Okay. No heat transfer. So Q is 0. So it's a insulated system. Okay? So insulated. So keywords in a problem would say an insulated container. Hence, Q is 0. I'm going to write this heading, but I just want to make sure there's a heading. Heat transfer is kilojoules per second. So you have Q, big Q, you have little q, and you have Q, little q dot, or big Q dot. If it has a dot in this class, it's per unit time. So remember that, all right? So if I have, I don't know, let's do a number here just real quick. Say our Q dot is 100 joules per second. And in 1 second, how many joules do I have? In 1 second, 100, right? Because you just multiply by 1 second, and you end up getting Q, which is 100 joules. Everyone see the difference? So the equation actually that we'll use to find Q without the dot is this. So big Q, the integral of big Q dot times dt. Why is it an integral? Anybody want to know why? Guess why? Well, you might want to know why. Because, yeah, the rate something comes in could fluctuate per unit time, so you have to integrate. We won't do any integration. It's going to be kind of simple stuff, so because concept-wise, you got to get through it. But that's the fundamental equation if you want to know how much heat has come over per unit time. So when Q is greater than 0, you have heat transfer to the system. So it's positive. When you have Q is negative, heat transfer from the system. When we get to the first law, this is important, knowing your direction. Is it heating up or is it cooling down? And you want to identify. So the bottom line for heat or heat transfer is In this class particularly, it's either going to be given to you in a problem or you're going to be asked to find it. Okay, so I'm not going to give you those. I'm not going to have you use the conduction, convection, and radiation equations because it gets even more complicated. Questions on heat? Okay, so let's look at work. So, do you remember the basic definition of work in physics? Yeah, force times a distance, okay? It is sort of usable energy. So a force acting through a distance. Dynamics students, someone take my dynamics already? Some of you are in it right now. We're going to get to work and power later on. So you're just regurgitating or whatever that word is. Everything. You're going to see a lot of classes overlap, but we look at things differently. So, for example, here's a piston. And we'll look at this more detail here in a second. It can move in and out. So that's work. In electricity, you have voltage running through a resistor, right? That creates power. Or you can have shaft work, a motor spinning a shaft. These, just a piston moving in and out. Yep. Oh. Erases the whole line. Oh, that's good to know. We'll get into the equations for specifics, but I want to talk about the basics first. I'm pretty sure we do. Bless you. Bless you. So we have a force. It's randomly applied along a distance. How do we find the total work? Integrate it, right? Yes. This is the fundamental equation for work. Force, the integral of force times dx. You have to integrate if the force is fluctuating. Oh, do I want to do that? Let me just do that and skip that one. Questions? Okay, so let's look at the piston a little bit more to help you identify positive and negative work. So here, the piston is moving to the right. All right. So the piston is doing the work. So let's write that. And when the piston does the work, you get negative work. So we have compression here. We can put compression as a heading. And the other one over here is expansion, or expanding. So I'll try to decipher or kind of help you. When I talk about work, I'll try to put the tails on the W because the other W is for watt, for power. So I'll try to make sure I'm clear on that. But if you have questions, just let me know. So when the system, the air inside there, for example, is actually causing the piston to move, okay, then it's positive work, meaning the system does the work. Where on the left, the piston is actually doing the work onto the system. So that's the biggest thing. Just remember that. When we get to the first law, we'll talk about it more, but it's just a good idea of, okay, what's happening here. And there are equations that I'm not going to show you yet, because it's a little bit more detail, about what are the work equations for this. We won't deal with that yet, because that's a whole separate section in the book. All right, it has to do with pressure and all that stuff, and volume change. We'll get to that later. What I do want to show you is, this is like the first chapter kind of deals with some basic stuff, is electric work or power. Did I skip power? No. But we can get to it. Before I show you the electric work, we can put it on here. W dot is for power. So we can put the unit kilojoules per second. And basically, it's your work over a change in time. And look, it's very similar to what? Heat transfer, right? You want to know how much total work is when you have a power that's changed as a function of time? So that's the basic definition of power, which you kind of need for electric and shaft. What is the power going through a resistor? What's that equation? Anybody remember? IV, yep. So I'll label it WE for electric. So I call it VI. You can call it IV. Doesn't matter. IV would make more sense. It would kind of remind you that's an IV shooting through you or something. And how would you calculate the actual work? What would we have to do? Just multiply by a change in time? Trust me, that will get everyone. Which one? Yeah, that's power. So this is power. And this is work. So yeah, that's what I'm trying to make sure you're clear, the difference between the two. And then the last thing I want to talk about is shaft power or work. It doesn't really matter because you can get either one. Oh, sorry. So I'll call shaft work WS, and that's 2 pi N dot times T. This is RPM. This is your torque.